Okay, yeah, good afternoon, everybody. Yeah, welcome to my presentation. I know you're waiting for the happy hour beer, so I don't make it too long. I hope we can finish more or less on time. Well, my motivation for this is that I love three things to do. I love filter design, I love to do Python programming, and I love microwave office. And I try to bring all the three of them together. A lot of the techniques have been mentioned already today. What Dan did is similar to what I do. That's why I'm trying to focus a little bit on the Python part. That might be the new part on this workshop today. Okay, let's see. Is this working? Yeah. As I said, I bring together two worlds, microwave office and Python. The good thing about Python is you can do basically everything with it. No? So you have a numerical solver and symbolic solver. You can build GUIs with it. You can do plotting. You can import and export to any other kind of things. You can put it on the web and so on and so on. So there are millions of different ways you can deal with that. Okay, let's see. I would like to concentrate on two or three things. First, how to do the Python integration. Second, how to do analysis and optimization using coupling metrics, using this Python back engine basically, and doing a full EM with Analyst, or actually with Analyst or with AXIEM. Actually, I did it, and integrate the whole thing. And if you have some time left, I would like to mention vector fitting, which is kind of a rational function approximation method. No? Okay, so let's see how do we get together Python and microwave office. I just put one slide on here. What you need AWR microwave office, of course. You need Python, of course, and in Python you need, well, you can install it if you want to do it in Microsoft Windows. It's easiest to do just to use this Anaconda package manager. So go to anaconda.com. Download the package manager, and then you can install Python. And if you like to do so, you can also install other things like NumPy, numerical solvers, SymPy, symbolic solvers, matplotlib for plotting, and so on and so on. So there are millions of things you can do with that. So how do you create the link? Basically, you start Microwave Office with an empty project. You don't even have to do that. It generates it automatically. Then you start your editor for your Python or IDE. And then you have to put these two lines here, import Win32 client, which imports the module for doing the API link. And then you define an object, I call it AWR DE for Design Environment, and then say you create a client, dispatch it to the app microwave, MWO app microwave office. So, and if everything is working, I can show you this in live. So here you see microwave office, yeah? And on the second window I have my Python IDE running, which is Jupyter, which is running actually in a web browser. That's why I waste a lot of space here right now, and because I made it a bit bigger too. So, but I think it's fine. Okay, so it's basically an interactive way of using Python. No? So you type in a command, you get something back. You type in a command, get something back. It's all running in a web browser, so you can go back and forth. It's easiest to show you things here. Okay, I start with a command called pylab inline, which just includes all kinds of interesting tools like NumPy and matplotlib. So then I do the two lines here. I execute them. I just mentioned, and then I have to create a schematic, and the schematic I just create here by saying, well, I have my AWR DE object, and I say project schematics add down here. Sorry, this one. Up here, these two lines are only there because when I have one already, I want to destroy it first. Otherwise, I end up with lots of schematics when I show it to you 20 times here. No? So basically, by executing this, I create an empty schematic here called filter. No, it's there. So, and now I can add elements to it. My schematic I just called S, and now I say this S object, I can say S elements add, and when I want to add a port, I say port position is 0, 0, 0. False, I forgot what is 4. You can do some, flip. I think it's, yeah, exactly, yes. Yes, yeah. So you can do flips and so, yeah. So the third one is a rotation and this one is a flip, no? Exactly, thanks, yeah. So, and then I can add an inductor, I can add a capacitor, another inductor, another port, a ground at different positions. Here this port, for example, I rotate it 180 degrees. So when I execute that, you see that actually it creates a port, inductor, inductor, port, capacitor, ground. Exactly as I defined it here, no? That's all. So that's automatically generates the circuit exactly the same way you do it with Visual Basic with a built-in macro editor, no? Yeah, now you have to set the values. What I did is I just use an example here for the low pass. Typical value from a table. I set the values to L, C, and L as L1, C2, L3. These are the values I calculated here. I type that in. You see here, the values are in here, no? They are not rounded off, that's why they are so big, so many digits here. So next step is we have to create a frequency sweep. I just call it here vals for values, and in Python I can create a swept array by just saying here from 0 to 4, 201 points, including the endpoint. I clear my frequency range, and then here I add an array according to the AWR system, no? Oops, I'll just do it like this. So, okay, there's nothing to see here. Maybe we have to open it up. And here you see the frequency values are set, no? Okay, next thing is adding a graph. Same idea, plugging in all the microwave office commands for it. Simulate it. Oops, I have to show it here. Simulate it. Oops, here you set up the simulator, and down here you analyze the circuit. No. And then I set the scaling, and then you get a graph with a complete simulation in it. No? So now I can keep going with all these things. I can add markers, for example. I can change the colors of the graphs and everything. For example, here I added markers. You see the markers up here. And actually I can read out the markers, because the next step is I would like to get the data from Microwave Office to do something with it. No? So I can just say here add marker, and then I read the value of the marker, and I see here at 500 megahertz and 1000 megahertz, these are the dB values. No? So next step would be to get the complete S parameter sweep. No? As we talked earlier about this morning, there's no simple way to just say grab S parameters. What you have to do right now is you have to create a Smith chart or a table, because you need the complex data, and then you just grab the data from the graph, no? And that's what I'm doing here. So it's all in the slides which you're gonna get, so you can just copy it when you want to at home. So this creates here a Smith chart, which is here with the response, and for me important, it's only that I got all the data, and I get like 2 Python lists now with S11 and S21, for example. No? So, and there's an error. Oh, it complains that Smith is already in use. That's exactly the point here. It creates a second Smith, I guess, or no, it doesn't. It actually overwrites the old one. So, okay, now I have all my data, and I can do whatever I want with it. No? And that's where the interesting part begins. Now I have everything in Python, and I've written my own modules for filter synthesis, filter analysis, vector fitting, all kinds of coupling matrix manipulations, and so on. And now I have all the data in Python, and I can play with it. No? One first example would be, for example, I can create the same plot now easily using Python. So I get this the plot of my low pass here now in Python. It's a bit fuzzy because I scaled it. Okay, so that's how you create your own Python simulations using Microwave Office. So I go through here in case that was my backup in case everything fails. How do I figure out what commands to use? No? For example, people kept asking me, how do you know you have to say here G measurements at? Well, it's all written in the API guide. Oops, I have to go up here again. There's this 1,111 pages document from AWR called the API scripting guide, and in there is every command you can use for accessing Microwave Office from outside. So basically it's a description of this so-called COM engine, as it's described here. You can connect it to all kinds of things, and Python would be the ... here. So, okay, good. The plotting I've done. One thing I like about it is I think the Python plots look more sexy than these ones. No? So I apologize for that. So if you want to put it into some publications or so, I like these plots, but I like those even better. So, sometimes publishers complain if you put in like something like that. So, okay, so what I can do with it, I prepared like 2 examples. First one is well, if you want to do something which is uncommon, which is not in the normal library of stuff or from new hertz and so on, and I came up with a funny filter. I don't know what it's good for. Please don't ask me. Just to have an example, I call it the accordion filter. So it has these wedge-shaped resonators here, and they are coupled here in between, input-output coupling, and for some reason I want kind of filter that looks like this. For example, here the ports are in this angle or something like that. It looks similar to a hairpin filter, but usually those are flipped. So the coupling is different. Let's go here to my, what I call it, fan filter. Same thing again as I've done before, and now I'm free to do anything I want. For example, I said I want a two-order filter. My angle between my wedges should be 25 degrees. And then I create the G parameters, and I'll tell you more about how I get the G parameters from a filter. So I kill my old fan filter, I create a new one, and now I have this for loop where I create all these couplers and lines and bends and put them all together. So when I do this here, hopefully, oops, I have to do it like this. Hopefully it works. So I create a new schematic called fan filter, and then this creates a thingy here. And when I look at the layout, I get this two-port filter with 25-degree opening angle. If I want something else, now I can, let's say I want a 6-pole and I want 40 degrees. Just a matter of clicking, and then I get this thing here, and when you look at it, you get the 6-pole with 40 degrees opening angles. So that's how you can create more flexible designs easily. Okay, let's go back to my 2-port here. So let's say now I'm back to my 2-port because again, I can simulate it here using my simulation tool, and I see this typical 2-port response. Okay, now let's go down here again. I go directly to my next thing. So from this filter now, I would like to extract the coupling matrix. When I get the coupling matrix, I know what the input and output couplings are, and I know what the interresonator couplings are, and I can play with that. And it's similar to what Dan has shown you earlier this afternoon. Well, it's not even similar, it's more or less the same. But what I do is I don't use the internal ports, I just grab the complete response and I extract the coupling matrix using a least square optimization from it, or use a vector fitting and I get the poles and zeros and so on. So there's a lot of math behind it, which can be done in Python quite easily, which I'm not going into. But what I'm doing now is first I get my response here from Microwave Office. So my response now is stored in Python. Now I generate a coupling matrix as a default value. I'm coming from filter tuning. They call it the golden filter there. So this is my 2x2 matrix, a 2x2 filter coupling matrix with including input and output couplings. Here, this input coupling, inter-resonator coupling, output coupling. All resonators are tuned at 0. And that gives me this solid line here. And the dotted line is actually my Microwave Office simulated filter. And you see the two differ. This is a phase. And now what I do is I have basically it's only one line here, M extract. So fit to M. No? This extracts my coupling matrix from my measured response by comparing it with my golden response. And that's done in the background. And now I get a new coupling matrix here. And this coupling matrix represents my measured or my simulated filter. No? You see now that the two curves match more or less perfectly, and they start to differ at frequencies way beyond my passband. And so this basically is my coupling matrix for the measured or simulated filter. Why does it differ? Dan mentioned it this morning, or not this morning, this afternoon. This is a narrowband approximation with coupling matrices. As soon as you go away from your center frequency, you get errors. No? And that's a very typical thing. There's no way a coupling matrix can represent this effect here, no? Because this is due to the transmission line length and not due to some lumped element. No?
It doesn't know about tangent theta.
Yeah, exactly. And now the cool thing is, once we have all of this in place, we can just say, okay, why don't we just vary the geometry of my filter and see how the couplings are changing? No? Similar to what we have seen this just after lunch. So now it does my simulation 10 times. You see it pops up, and it extracts a coupling matrix, and I see I made a mistake here. See, no problem. No, I don't. Okay, so that's done. What I do is, this is for 1 millimeter gap in the. Maybe I go and take a look. So what I'm doing is, let me just search it. As you see here, I'm varying. I have to snap it together in order to see it. I'm varying the distance between these two resonators here, no? From 1 millimeter to 5 millimeters. So at 1 millimeter, I get this coupling matrix. For 1.1, I get this coupling matrix, and you see that actually this coupling M12 keeps changing here, no? 108, 101. That's because the M12 coupling must change because the distance between the resonator changes, no? So once this is done, I can make a plot out of it. Plots are easy to do, and I get my dependence of, it's a little bit too small here. I get my dependence of the coupling. It's labeled wrong. It should be M12, sorry. So this is the coupling M12 with respect to the gap size. No? So, and I can repeat this step for the length of the resonators, for the input couplings, and so on, and then I can get plots. Or even more, I can actually extract. I make an approximation using a cubic spline here or a cubic function. I can get all these graphs, and then when I want to create a different filter and I know what the couplings are, I have a lookup table similar to what Dan said rather than having capacitances or coupling values, I have millimeters. No? If I need a coupling of 0.8, I know I need a gap of 2.6 millimeters, no? And then I can do that. No? Using this trick, I created a 4-pole filter. So this is my coupling matrix now for the 4-pole filter. Again, I just say in my Python script here, I want a 4-pole filter with 0.5 dB ripple and so on, bandwidth. That gives me my coupling values, and this is my ideal response, how it should look like. I calculated all the gaps here, and then I plugged them in, and this I prepared already here. And from that, I can create now, for example, a 4-pole filter. No? So when I go now here, I have another schematic called FEM. I created a new one, sorry. I hope that works because I haven't, yeah. So now I got a 4-pole filter with the gap distances I grabbed from my tables I created. And I get a response, and this is my response that's generated from that design process. No? So this is, first step. Now we can do some final optimization, but it's really close to my ideal one, which is this one. And I didn't change the resonator length, which I should have done, and that's why it's not a perfect fit here. Where's my reference? So it should. Oops, sorry. Oh, I'm on the wrong one. It should look like this, no? As a 4-pole, but I get this now, no? Okay. So this is the process of using Python, extracting the coupling matrix, getting tables or graphs, what the couplings are, how the couplings are related to the geometry, and then you can go backwards and create your own filter for whatever you want. No? Any questions here? So I can type in or whatever. So okay. Then if not, then let's go to the next step here. I have another example which goes a little bit further. The starting process is more or less the same as I showed you. I just used this comline filter here. It's a 3-pole, 0.5 dB ripple. Again, I used my Python algorithm to just say, okay, my filter is a Chebyshev filter with this order, and I get my coupling matrix. Then I start with some geometry here I think is good, and I plug that into my microwave office model for a comline filter. I put in all the numbers, difficult to read, but I put in some numbers, and I get this response here. No? So this is no good. This is not my Chebyshev I want. So what I do is I go through my Python code, set the parameters, create a geometry, simulate, read the response, extract the coupling matrix, and display the coupling matrix, and I see this is the coupling matrix I get from this simulation here. No? And you see also there's a transmission zero from some parasitic coupling here between some of the resonators. No? So, okay. Now I can do the following. I can do either the same thing Dan did, which I do later in the slides, or I can just go ahead and create the charts for the couplings. No? Again, as I showed you 5 minutes ago, I vary my length and the gaps here and so on by doing this loops here, and then I can plot the charts, and I get it. So I can get a chart for the input gap, which represents a coupling, for the inter-resonator gaps, which represents these couplings, and I get also the change of the self-couplings, M11, M22, and so on, depending on the resonator length. No? And this should be fairly linear, and it is actually. No? So and from this, I can just say, well, this is my desired coupling matrix. I want an input coupling of 0.79, so I look at my chart, and I get gap 0.58. And for my inter-resonator coupling, I get this. My resonator length, I get this, and then I get these values here for my S and my L. No? Same process I've showed you before in the live demo. No? And when you do that, you see actually it works out. You get exactly your 3-pole Chebyshev you want, and you still have this extra coupling in here, which you cannot get rid of, which is actually nice, no? So you get a sharper response. And this is my extracted coupling matrix. You see that these values 0.788 are very slow, very close to 0.79, which was the ideal one. No? Okay, this is not really the final thing because it's still easy. Now we know that it's not exactly as I want it. Now I can do the following. I can look at the coupling matrix of the realized filter. I can look at the coupling matrix of the golden filter, and I look at the difference between the two. And then I get this difference coupling matrix. And you see from the colors, white means they are on track, and red means they are too big or too small. And now in the next step, I can just correct for that and get it even better. No? Another cool thing about that is it doesn't have problems with losses, so you can do the coupling matrix extraction also with losses. Every resonator has its own queue, and we're just going through the Python code, including the losses here in my substrate. I get this response, and then you run the code, and it tells you there's a filter queue of 244. No? From that gives you this response. Okay, now last step. We can do the same thing using Analyst. Then when you get the response, it's even worse because it is a full EM simulation, takes a lot of things into consideration. I compare my simulated filter with my golden filter. The simulation now is a very tedious task. No? It takes, I don't know, not too much for this filter, but it takes minutes. No? And the golden, that's why we want to avoid these steps. We get from the difference, we see how my real coupling matrix differs from the ideal one. And now I can do the same trick Dan showed you earlier. Once I have the difference and I know the slope of my geometry, I can adjust for it. I called it space mapping, you called it calibrated something. Yeah, you could call it space mapping, but it's not exactly space mapping because space mapping is more general. No? It's more. Yeah. So yeah, and I had to do a lot to do with John Bandler, so I call it space mapping. But that's the idea, no? So you have the real values and you have the map values. And by doing, I just need like 3 iterations, no? And the 3 iterations bring me to this full EM simulated response, no? So you do a 3-pole planar filter with 3 EM simulations, and you get it on right on, no? Which is okay. Good. You want one more? I just tell you one more thing, and then I'm over. Okay. That's called vector fitting. It's interesting because that's the only thing that hasn't been mentioned before today. There's a process called vector fitting here, invented by Gustafsson and Semelian, where you can use measured data and you fit them to a rational function approximation, or basically a fractional, what do you call it, a fractional polynomials, no? And when you have those, you basically have the transfer function in an analytical way, yeah? So it's not, you don't get a bunch of data, you get your pole positions, your 0 positions, you get everything you want, and like the filter theory guy is really pleased having this, no? So, and I show you just in a very quick demo here how it's done, and then I think we can leave it like this.
They were looking at power systems when they developed?
They did actually power systems. They had transformers, and these transformers, they actually have a lot of resonances because of the windings and so on. They want to know where the windings are and how they can move them, and that's why they came up with them. They actually, and when actually I started using it because I talked to my power engineering guy, and he said, like, that's interesting stuff, and I used it, and then as usual, like a couple of months later, other people popped up with the same idea from the power engineers. So, and it works really nicely. So, just to show you how it works, here I have my. Remember, I have my 4-pole filter. I just use this 4-pole filter. I want to know what the poles and zeros are from that filter. No? all I do is I start my vector fitting. That's so this is just to get the values into Frank. And here, this is my self-written vector fitting algorithm, which is not big, so it's just a one-liner in Python now. When I click it, it gets me the residues, the poles, and the rest of the function. And I can just click it here, and you see the blue line is my measured data, and the red is my racial function approximation, no? And here's the face, and you see it's right on, no? So basically, you get exactly you exactly get the response. And here you see I plot the poles of the filter, and you see this nice typical Chebyshev ellipse, no? Shape, no? And you see they are not exactly straight because my filter is not perfect, no? So what you can do now is you can move your poles around if you want to the place you want it, no? And it also works with transmission zeros. I didn't have time to show, and it shows up the transmission zeros as well. Okay, and then also you can do what you can do is you can plot your transfer function, or you can also plot your transfer function as a rational polynomial, which is kind of fuzzy here because there's so many digits in there. But that's your transfer function of your filter, no? And now you can use it also to extract the coupling matrix directly from that, no? That's cool. Okay, I think that's more or less it. I have this similar example here, and I'm open to more questions about that now.